the technique of integration using substitution. Now we're going to look at lots of different techniques, certainly in extension 2. But in extension 1, this is pretty much the only technique we look at, is the substitution idea. That doesn't mean you can't use any of the ones we end up looking at in extension 2. You can still use them in extension 1. It's just that extension 1 don't see them. But the idea is to get everything into a form of a standard integral, because we're going to have an integral that we look at and we just don't recognize, and so we want to get it into a form that we do recognize and know how to integrate. The ones that do appear on our reference sheet that we get given in the exams, and they're the ones that are written in this format. So this was the very first idea we looked at when we have a derivative times some function to the power of n, and we can add 1 to the power of the power. This bit over here where n does not equal -1, it's just a formality, because of course if it did equal -1 you'd end up with 0 on the bottom of the fraction. That's probably when you're going to have a log situation. That's the derivative of a function. Then they have our trig ones. We know sine goes to minus cos, cos goes to sine, sec squared goes to tan. The exponential one, remember we want the derivative out the front, that's how we'd like to see it. Then there is that derivative on function 1 which goes to log of the absolute value. Remember the absolute value? The only time you wouldn't put absolute value in is if you are 100% certain that that function can't be negative. Otherwise you need the absolute value signs there. They also have the one where the base is not e, so reminder, you do it the same way, but you divide by the natural log of the base. And now we've completed our list of functions there. We now have our inverse trig ones. They only put inverse sine, but remember it could be minus inverse cos if you wish to. And then there is of course the inverse tan one, and that's the one where we must remember to go 1 on a out the front. But again, I'll mention it, they are on the reference sheet, so if you are unsure, it's there to help you. So make sure you look at it and go, oh yeah, make sure right, now I know. That's definitely the one I'm using. Let's now look at some examples. Now, the difference between extension 1 and extension 2 as well, they will give you the substitution. And I guess that's because in extension 1, what they're basically doing is, because this is the only technique really that they look at, they want to know that you know how to use the technique. So they force your hand and say, we'll use this substitution, so they can see, righto, you know how to do this substitution method. Whereas in extension 2, because you have a whole suite of different approaches, they don't really force your hand. It's up to you how you do it. Very occasionally they might tell you to. Sometimes they might just give you a hint and say, well, by using this or otherwise to help you along, but a lot of the times, no, you come up with it yourself. They've told me the substitution to use, but remember it's a complete substitution. All mention of x should be gone, and that includes the dx as well. So we need to work out the dx. So there's u sitting on the bottom. We've got that. Du would be 8x plus 8. Well, it's close to that. We've got a multiple of it. So there is sort of du, but it's actually 1/8 of it. So I know I could rewrite this as 1/8 of du on u. That becomes the log of the absolute value of u. It's now in a form we recognise we can do it. The reality I would say is this: if it wasn't by substitution, if they hadn't have made us use this, then in reality is I probably wouldn't have used it. I would have just looked at it and said, oh, I want derivative on function, like we've been doing. So, well, let's just create it. We would have got the same answer, of course, because this answer is not the final answer. It still has u in it. We need to substitute back, and there it is, 1/8 log of the absolute value of 4x squared plus 8x minus 7. If they had not given me the substitution and I wanted to use that method, I would have looked at it and said, well, what's causing me the problem? And the problem is that this log x is to the power of 3. And you'll find with a lot of these, usually the thing that's to some power, that's going to be the substitution I use. That happens in a lot of cases. So I would probably try that first anyway. U equals log x, so du becomes dx on x. Yeah, we've got that as well. Okay, I've got du on u cubed, which is u to the -3. Add 1 to the power over the power, sub back in, we got the answer. Here's one from an HSC from a few years back now, a definite integral. They told us to use the substitution u equals 1 minus x. Well, du becomes minus dx. But remember, we have to substitute into all mentions of x, including these limits. Now, it doesn't say x equals -3 and x equals 0, but that's what those limits are. So we have to change those as well. So substituting into the formula we've been given there, u is 1 minus x, I can see that when x is -3, u is 4. When x is 0, u is 1. Now I can do a complete substitution. 1 minus u on root u. It's still not quite enough one of the standard forms. So I will break this fraction up into two things, and I'll get 1 on root u minus the square root of u. And I've now got two things I can integrate. The 1 on root u, that becomes 2 root u, and the root u, remember root u is u to the half, so it becomes u to the 3 on 2, but 2/3 of that. I've gone straight in the third form there, 2/3 u root u. Sub in the 4, sub in the 1, we get our answer. Use the substitution u equals cos squared x. This one came from the 2019 HSC. Well, if u is cos squared, du becomes -2 cos x sin x. So we actually have to do something else before we can do this substitution, because you'll notice on the top here we've got sin 2x. Now, whether I change that sin 2x into 2 sin x cos x, or, how I've done it, change the du into sin 2x, it doesn't really matter. The fact is, now I can do my substitution. The limits need to be worked out, so I've got those calculated. Now I can do a complete substitution, and there we have it. Du on 4 plus u, I got a log situation. Now, I suppose technically you could have done another substitution as well and gone, oh, let I don't know, v equal 4 plus u, so no, I wouldn't bother with that. I can see I've got derivative on function, so we have log of 4 plus u. You'll notice I didn't put the absolute values on this one, and that's because I sort of looked ahead at the limits and said, well, yeah, these are going to end up being positive numbers, so I don't really have a problem with this one. Subbing in, we get the log of 10 on 9. Absolute value signs, I guess the safest bet is just to always put them there. And then you don't have to do that thought, oh, is this going to be positive or not? And if you've got the absolute value there, it just solves all your problems. Okay, 2017. This one's another way we can do the substitution. Instead of substituting u equals, they actually make it x equals, and you sub straight in for x. So x is u squared minus 1. When you do this, you've got to be careful with the domain. Now, here's not an issue. Remember what I was talking about the other day is if you have a discontinuity in the domain, how the function value might be different on one side of the discontinuity as the other. Discontinuities can cause problems. Now, this particular function, it's not a problem, because I can quickly look at this and see, well, the domain of this, x plus 1 must be greater than 0, so x is greater than -1, both of these, so it's continuous from 0 to 3, I haven't got an issue. Doesn't come up a lot, but it's just something to be aware of. So x equals u squared minus 1. That's the same as saying u is the square root of x plus 1. So the advantage of doing this substitution is the whole square root will go away on the bottom of that fraction. Dx will be 2u du, and I can just sub that straight in for dx. And I've still got to work out the limits. So I guess that's also another reason why over here I made u the subject, so I can very easily work out what the u values are going to be when I substitute in. So now let's substitute in. X becomes u squared minus 1. The square root of x plus 1 becomes u. The dx becomes 2u du, and my limits. Tidying that up, I've just got a little polynomial to integrate u squared minus 1. Add 1 to the power over the power. Substitute in. We have our answer. So this is the idea of integration by substitution. Let's do a whole handful of those.